Good morning, welcome to another session with me, Srilekha, lecturer in Mechanical Engineering, uh, Agraharam, Telangana. So, in the previous classes, we have discussed something regarding the stresses and strains and etc. So, in today's class, we are going to discuss about uh, temperature stresses. So, temperature stresses. Now, in the last class, we have discussed about the analysis of composite bars and analysis of the varying cross sections of the composite bars, etc. Hope you are all clear with the previous topics. And today we'll go for thermal stresses, temperature stresses. So, when does this temperature stress occur? So, when a material is experiencing so, due the change in its temperature, or whenever it is expanding or contracting due to the change in temperature, then then their stresses are occur. So today's class we are going to discuss about temperature stresses and some problems regarding the temperature stresses and also temperature stresses in composite bars as well as problems related to the composite bars. So first let us study what is the temperature stress actually it is. So when a material undergoes natural or free expansion due to the rise or drop in the temperature, then there is no strain and therefore no resistance of stress. So if it is going for a natural or a free expansion, say if this free expansion or contraction is occurring due to the change in the temperature, it is not occurring naturally, but if it is occurring due to the change in the temperature and this temperature is preventing the external forces like by holding the end groups, then stresses and strains will be set up. So it is occurring only when the free expansion or contraction due to the change in the temperature is prevented by the external grips, external forces, then only these stresses and strains will be occurring. So these stresses are called temperature stresses. So for this temperature stresses, we know that every material expands with temperature rises and contracts when the temperature falls. And the change in length due to the change in the temperature is given by equation delta L equal to L alpha T. So delta L is change in the temperature, L is the length of the bar, alpha is the coefficient of linear expansion, and T is the change in the temperature. So this coefficient of linear expansion or the thermal expansion uh, is different for different material. Okay, so if this expansion is permitted free from no stresses, uh, then partly if the stresses are induced in the bar, then we may call it as temperature or thermal stresses. Now if these temperatures are fully inducing certain stresses, then we will permit up to a yield. So here we are going for two cases. First one is the stresses are partly induced. then you have one formula, and if the stresses are completely induced, then we have another formula. So for instance, let us take a bar of length L. So a bar of length L and whose cross-sectional area is A. He is heated through a range of T degrees. So but it is prevented by end grip. So if you see here, it is not, it is prevented by end grips. It is freely fixed. So then what happens when gives from expansion? Then what happens? This external force of P is acted upon by the end grips. So by the ends. Okay. So this load, it will cause compression in this particular body. So if it is compressed, if it is acting towards the ends, then it will compress the body, and the bar will have to offer the compressive stresses to resist this force P. Right? Now, so here uh, the magnitude of that particular force, so its role is to decrease the size of this bar, right? So it will just shorten this load which is acting, will just short, it will just shorten the size of the bar, and this size of the bar, or this change in the size of the bar, is given by the formula L alpha T. So we know that compressive strain, here the strain occurring due to the compression, is nothing but change in length by original length. So change in length is delta L, original length is L. So delta L by L, so here you can see, so compressive strain is change in length by original length, that is delta L by L. So delta L is L alpha T. We already know the formula by L. So the compressive strain is simply alpha T. But we know that the compressive strain is alpha T, and we know that the Hooke's law, stress by strain, is nothing but the modulus of elasticity. Now if I want temperature stress, so I'll just substitute this strain alpha T in place of strain. So your stress will be sigma equal to E alpha T. Okay. So E alpha T is the stress. Now if I want to find the compressive load exerted by that particular clamp or that particular end, it is simply, we know that stress equal to load by area. So therefore load is equal to stress into area. So you can see, so here W is the load, so stress is E alpha T into area is A. So load is equal to stress into area. Okay. So in this manner we are going to find calculate the values. Next, so if the temperature stresses are fully induced, it means one end is clamp and the other end is left with certain clearance. Now it means that the left side end is clamped and the right side end is left over for the clearance. So this end is free for expansion. Say now, so here what we do, the effective compression or the change in the length is simply, so previously the change in the length was L alpha T, but we are partly uh, opposing the strain. So we are partly opposing its elongation. So that part is simply delta. So here the total elongation or this compression is simply delta L, means this line. Okay. So what is this value? It is simply total L alpha T minus delta. So L alpha T minus delta. Okay. So it is L alpha T minus delta, where delta is the small clearance that is given due to yield. Okay. So due to yield, that is the clearance given. Previously it was simply L alpha T. Now the strain is as usual again. Strain is equal to delta L by L. So L alpha T minus delta by L. So L and L gets cancelled for the first numeric value. So it will become alpha T. And for the next one, so it is simply minus delta by L. So this is strain. Now if I want a temperature stress, so stress is again, stress is equal to modulus of elasticity into strain. So instead of strain, we'll substitute alpha T minus delta by L. So therefore stress sigma is equal to E into alpha T minus delta by L. So this is how we calculate when yield is permitted. Okay. So now let us discuss few problems. So two parallel ways 8 meter apart are stayed together by a steel rod 25 diameter, passing through metal plates and nuts at each end, which are tightened at 120 degrees temperature. Determine the stress induced in the rod when the temperature falls to 40 degrees centigrade, if the ends do not yield and if the ends yield by 2 means here full expansion or free expansion and the other one is partly expansion. See, given that two parallel walls which are at a distance of 8 meter, they are fixed by or they are stayed by the steel rod. So this steel rod diameter is 25 and the distance between the two walls is nothing but the length of the rod. So the rod is connecting these two parallel walls. So up to what distance? It is up to 8 meters of distance. So the length of the rod becomes 8 meters and the steel rod, its diameter is 25 Now this is passing through the metal plates and nuts at each end. So at each end this steel rod is tightened at a temperature of 120 degrees. Now you need to find the stress induced at a body when temperature is decreasing to 40 degrees centigrade. So the ends, if two ends do not yield and if ends yield by 2 For steel, the modulus of elasticity is uh, 2 into 10 to the power of 5 Newton per square, and the coefficient of linear expansion is 12 into 10 to the power of minus 6 per degree centigrade. Okay. So we understood that the diameter of the rod is 25 So its area can be calculated by pi by 4 d square. So nothing but pi by 4 into 25 square. Next, given that both the walls are apart from each other by a distance of 8 meters. So it is 8 into 10 to the power of 3 Next, so coefficient of linear expansion is given, that is 12 into 10 to the power of minus 6 per second. Next, modulus of elasticity is given, that is 2 into 10 to the power of 5 Newton per square. Now, so let us take change in the temperature. So initially it was 120 degrees at which both the ends of the rod was tightened with the help of metal plates and nuts, and later on it cooled to 40 degrees. So the difference in the temperature is 120 minus 40. So it is simply 80 degrees centigrade. Now the stresses induced when the ends do not yield. So it is the first case which we discussed. So we know that stress is equal to strain into modulus of elasticity. But the strain means alpha T. So alpha T into E. So that is equal to 12 alpha value is 12 into 10 to the power of minus 6 per second into t t value is 80 and this modulus of elasticity is 2 into 10 to the power of 5. So it is a printing mistake as 20 into 10 to the power of 5. It is simply 2 into 10 to the power of 5. So this on calculating everything, you will get a value of 192 Newton per mm square. So this is the stress induced when the ends do not yield. Okay. Next, so stress induced when the if the ends yield by 2m. We know that strain is alpha t minus delta by L, where delta is the yield, right? So now stress will be simply alpha s t minus delta by L into E. So E value is 2 into 10 to the power of 5 into 12 into 10 to the power of 6 into 80 minus 2 by 8000. Okay. So on calculating all these things, you'll be getting 142 Newton per mm square. So this is the stress induced if the body is partly is prevented partly. Okay. Now the pull exerted, nothing but the load applied on the bar is, so the load equal to stress into area. The stress induced if there is no yield, then it is 192 into pi d square by 4. Now the stress induced when there is a yield, then it is 140 into pi into 25 square by 4. So now the load acting is 94,200 newtons, 94.2 kilonewtons, and here it is 69.66 kilonewtons. So the load more acts when there is no yield, and even the stresses developed are very high when there is no yield. When it is without yield, if it is with yield, then the stresses developed are less, and also the load effect of the load or the pull is also less. Okay. Next. So if at all a situation comes like this, okay. So if a steel rod 2 meter long is fixed rigidly at the ends and heated through a temperature of 100 degrees centigrade, find the stress induced in the rod if alpha s is equal to 12 into 10 to the power of minus 6 per degree centigrade and Es is equal to 2 into 10 to the power of 5 Newton per mm square. Now what is the expansion prevented? Right? So let us take now, given that the length of the rod is 2 meter long and this is fixed rigidly at both the ends and heated to a temperature of 100 degrees centigrade, right? So the length of the rod is 2 meters, so it can be written as 2000 mm, and given that increase in the temperature, nothing but it is heated up to 100 degrees centigrade means the increase in the temperature is 100, say. Now, given that alpha s, nothing but coefficient of linear expansion, is 12 into 10 to the power of minus 6 per degree centigrade, and modulus of elasticity is 2 into 10 to the power of 5 Newton per mm square. Now we need to find the stress induced in the rod. So stress induced in the rod, how can you find? So we know that stress induced equal to strain into modulus of elasticity. So modulus of elasticity is given. You need to find strain, right? So it is change in the length or elongation or shortening in the length is L alpha T. Right? Delta L is equal to L alpha T. So that is equal to 2000 into 12 into 10 to the power of minus 6. Right? So that is equal to 2.4 mm. So by 2.4 mm of length has been shortened due to this. Okay. Next, strain. So strain is simply change in length by original length. So what is the change in length? 2.4 by uh, it is simply 2000. So that is equal to 1.2 into 10 to the power of minus 3. Or also you can write alpha into t. Strain formula is alpha into t also. So it is also simply 12 into 10 to the power of minus 6 into 100. It will also give the same value, that is 1.2 into 10 to the power of minus 3. Now stress induced is equal to strain into modulus of elasticity. So strain is simply 1.2 into 10 to the power of minus 3. Modulus of elasticity is 2 into 10 to the power of 5. So now the entire stress induced is 240 Newton per mm square. So this is the value you get. Next, so temperature stresses induced in the composite bars. So here it is given. First let us see A. So composite bars are nothing but if the, what is a composite bar? Okay. So till now we have explained explained the simple bars, single bar. Now if it is a composite bar. So composite bar is nothing but the um, which contains more than one type of material. Sometimes brass bar or brass casing and a steel bar or a brass tube and a steel rod. So like that it means which comprises of two kinds of material or more. Right? So so if you are considering a unit length of compound bar, a compound bar is nothing but the bar which is made up of two or more kind of materials. Compound bar, and let elongation be delta L under the rise of temperature. Now if I take some material bar, it is pulled by some casing, say. It will stretch with natural expansion. Thus, it will suffer the tensile strain. Now, the tube in which will not be able to deform to its full natural expansion, it will being restrained by the rod. So, with less coefficient of expansion. Therefore, the tube will be in the compressive strain. Okay. So now let us take it. So that is what you can see here. If I take a bar of two materials, so this is one and this is two. If it is a composite bar, I am heating it. Then what happens? The bottommost bar, it will expand up with a freely. It will expand it to its maximum uh, point of expansion, whereas the upper part, it will not expand completely, or the inner part will not expand completely, because the stresses induced in the bottommost part, they will act as a compressive load for this topmost part. So you can see in the next diagram that, so the first part is increased by delta L, whereas the second part is increased over the delta L2. Okay. Next, if we are fixing them, means if we are holding certain end of it with some joint or rivet, or if you are holding it, then what happens? Then the material will uniformly be deformed. It means the length of the both the materials will be same. Now, so when a composite bar of two materials is heated, then they experience different types of expansion if free to do so. Since these ends are rigidly fastened together, so they expand to an equal length that is given in the figure C. Now, compressive stress in the bar 2 reduces its free length by x2, and the tensile stress in the bar 1 causes an expansion of x1. So, if there is no external loads applied to the composite bar at any section, then the tensile load in the bar is equal to compressive load in the bar. Okay, so tensile load in the first bar will be equal to the compressive load in the second bar. So tensile load in the first bar means stress into area of the first bar is equal to stress into area of the second bar. So now the so this is nothing but the formula for load. Load is equal to stress into area. Load equal to stress into area. Both the loads are equal. Now also free length of the bar, or the length by which it is decreasing or increasing is delta L1. So it is simply L alpha 1 T. Similarly, for the second specimen also, delta L2 is equal to L alpha 2 T. Now, if alpha 2 is greater than alpha 1, if alpha 2 is greater than alpha 1, then you can see that B diagram B. If alpha 2 is greater, then it will expand like anything. So, from this figure, it is clear that, so if I am taking some reference point at the center, it is simply delta L1 plus x1 should be equal to delta L2 minus x2. Right? So L alpha 1, so delta L1 is simply L alpha 1 T. Substituting instead of the delta L1 this value L alpha 1 T plus x1 is simply sigma by E into L should be equal to L alpha 2 T minus sigma 2 by E2 into L. Okay. So now instead of L alpha 1 T and L alpha 2 T, I am taking the similar terms on same sides. So it is alpha 1 sigma 1 E1 into L plus sigma 2 E2 sigma 2 by E2 into L should be equal to L alpha 2 minus L alpha 1 T. Now, so I'm taking L common on both sides, so it will simply get cancelled, and the leftover things will be delta 1 by E1 plus delta 2 by E2 is equal to T into alpha 2 minus alpha 1. So L got cancelled on both sides. Now by using these equations, so sigma 1 A1 equals sigma 2 A2, and sigma 1 by E1 plus sigma 2 by E2 is equal to T into alpha 2 minus alpha 1. So the stresses induced in the bodies can be calculated. So next let us go for a few problems in this. So a steel bar 6 into 10 to the power of 3 mm square cross sectional area is rigidly fixed with a copper bar of 4 into 10 to the power of 3 mm square sectional area. Both the bars are of 1.5 meters length. Calculate the stress in the steel and copper if the compound bar is heated from 115 degrees centigrade to 250 215 degrees centigrade. Take modulus of elasticity of steel as 2 into 10 to the power of 5 Newton per mm square, and coefficient of linear expansion of steel is also 12 into 10 to the power of minus 6 per degree centigrade, and EC is equal to 1.2 into 10 to the power of 5 Newton per mm square, and alpha C is equal to 18 into 10 to the power of minus 6 per degree centigrade. Okay. So given that a steel bar 6 into 10 to the power minus 3 mm square cross sectional area. So it is given in terms of its area, that is area of steel AS is equal to 6 into 10 to the power 3 mm square. So it is fixed to a copper bar which is of area area of copper AC is equal to 4 into 10 to the power 3 mm square. Given that both are of same length, that is L1 is equal to L2, that is 1.5 meters. So you can write it in mm. I think that 1.5 into 10 to the power 3 mm. Now calculate the stress in the steel and copper if compound bar is heated from 15 degrees centigrade to 215 degrees centigrade. So take ES is equal to 2 into 10 to the power 5 Newton per mm square. Alpha S is equal to 12 into 10 to the power minus 6 per degree centigrade. EC is equal to 1.2 into 10 to the power 5 Newton per mm square. The coefficient of linear expansion of this copper bar is 18 into 10 to the power minus 6 per degree centigrade. So given areas, we are writing area of steel AS equals 6 into 10 to the power 3 mm cube mm square. Now area of copper bar is 4 into 10 to the power 3 mm square. Length of the bar is 1.5 into 10 to the power 3 mm. Next, rise in the temperature is, so it is from 15 to 215. So 215 minus 15, it is nothing but 200. Next, modulus of elasticity of steel is 2 into 10 to the power 5 Newton per mm square. Modulus of elasticity of copper is 1.2 into 10 to the power 5 Newton per mm square. Alpha S, nothing but coefficient of linear expansion of steel is 12 into 10 to the power minus 6 per degree centigrade. Next, coefficient of linear expansion for copper is 18 into 10 to the power minus 6 per degree centigrade. Okay. So for free expansion of copper is greater than that of steel, but due to end constraints, both bars will expand with the same amount. So thus copper bar is under compression while the steel bar is under tension. Now for equilibrium, should take tensile load on the steel is equal to compressive load on the copper. Okay. So tensile load on the steel should be equal to compressive load on the copper. Now, so both the loads we have taken equal, that is tensile load on the steel is load is equal to stress into area. So alpha SAS is equal to alpha CAC. Both the loads are equal. It is simply alpha is equal to alpha C by AC by AS into alpha C. We are not given with the now, sorry, that is sigma S AS equal to sigma C AC. Mistake is given in the printing. So stress into areas should be equal, nothing but load. So stress of the steel is equal to 2 by 3 of stress of the copper. But we also know that both the strains is nothing but both the questions, we know that uh, L alpha T is equal to sigma S by ES plus sigma C by EC. Okay. So sigma C by EC. So sigma S by 2 plus sigma C by 1.2 should be equal to 200 into 18 minus 12. Okay, that is T into alpha C minus alpha S we have to do. So 1.2 into sigma S plus 2 into sigma C is equal to 2.4 into 200 into 10 to the power of minus 1 into 6. So from the equation alpha sigma S equal to 2 by 3 of sigma C, substituting it into the second equation, that is 1.2 sigma S plus 2 sigma C is equal to 2.4 into 200 into 10 to the power of minus 1 into 6. Then you will get sigma C value as 102.85 Newton per mm square. So sigma S value will be 68.57 Newton per mm square. Okay. So in this manner, we are going to find stress in the copper and stress in the steel bars. So next, a steel tube 24 mm external diameter and 18 mm internal diameter is enclosed to copper rod of copper rod of 15 so a steel tube 24 mm external diameter and 18 mm internal diameter enclosed a copper rod of 15 mm diameter. The composite bar is rigidly joined at both ends. Find the stresses in the steel tube and the copper rod. If the temperature of the composite bar is increased by 190 degrees centigrade, take E for steel and copper as 210 kilonewton per mm square and 110 kilonewton per mm square respectively. Also take for steel and copper as alpha for steel and copper as 11 into 10 to the power of minus 6 per degree centigrade and 18 into 10 to the power of minus 6 per degree centigrade respectively. So it is given that the steel tube rod, right? So this is a hollow steel tube which has an external diameter 24 mm and the internal diameter is 18 mm. It is enclosed with it means a copper rod is inserted inside it of diameter 15 mm. So this composite bar is rigidly joined at both the ends. Now if the temperature is increased by 190 degrees, now we need to find the stresses in both the bars. Okay, so it is as simple as it is. So everything values are given. Now let us find the required magnitudes. First, given that steel tube is an hollow one because it is having two diameters, that is inner diameter is 18, outer diameter is 24. So now area of cross section of the steel tube is pi by 4 into external diameter square minus internal diameter square. So pi by 4 into 24 square minus 18 square. So that one you will get a value of 197.82 mm square. Next, given that diameter of the copper rod is 15 mm. Now area of the copper rod is simply pi by 4 into 15 square. So now if I take, why did I do this? So now if I take this, if I take this, then modulus of elasticity of the copper rod is 110 kilonewton per mm square. So we can write that in Newton. That is 110 into 10 to the power of 3 Newton per mm square. So 110 can be written as 1.1 into 10 square. So it is simply 1.1 into 10 to the power of 5 Newton per mm square. Next, so coefficient of linear expansion is sigma c alpha c is equal to, so there are some mistakes, that is instead of sigma it is written alpha here. Alpha c is equal to 18 into 10 to the power of minus 6 per degree centigrade. Now we know that sigma s by es plus sigma c by ec should be equal to T into alpha c minus alpha s. Okay, so sigma s by es plus sigma c by ec should be equal to T into alpha c minus alpha s. So instead of alpha it was written s in this particular equation. So I am substituting the values. See, sigma s by 2.1 into 10 to the power of 5, which is nothing but modulus of elasticity of steel, plus sigma c by 1.1 into 10 to the power of 5, that is modulus of elasticity of copper, should be equal to T is nothing but change in the temperature, that is 190 degrees, into alpha c is 18 into 10 to the power of minus 6, minus alpha s is 11 into 10 to the power of minus 6. Now the total value becomes sigma s by 2.1 plus sigma c by 1.1 is equal to 19 into 7. So we are cancelling 10 to the power of 5 on the numerator and the denominator plus. So the equation is something like this. Sigma s by 2.1 plus sigma c by 1.1 is equal to 19 into 7. But we know that length is same on both the ways. Both the ways, the compressive load should be equal to the tensile load, whatever might be the load. So sigma s into ts is equal to sigma c into tc. Okay. Sigma s into as should be equal to sigma c into ac. It is not t, it is a mistake given. It is as. So sigma s as should be equal to sigma c ac. Now sigma s equal to ac by as into ac. Okay. Sigma c, small ac is not there, it is simply sigma c. Now if I calculate this, I'll get a value of stress in the steel bar is equal to sigma s is equal to 0.8928 into sigma c, that is nothing but stress in the copper rod. Okay, so we have two things, that is sigma s equal to 0.8928 sigma c, and one more thing is sigma s by 2.1 plus sigma c by 1.1 is equal to 19 into 77. So by making use of these two equations, by substituting the one into the other, by substituting first equation into the second equation or second equation into the first equation, you will get stress in the copper bar as 99.68 Newton per mm square, while stress in the steel bar as 88.89 Newton per mm square. So this is how we will be calculating the values. So in today's class we have discussed thermal stresses. So thermal stress induced in the composite bars are simply, you'll have two conditions. One is tensile load on the bar is equal to compressive load on next bar, that is sigma 1 a1 equal to sigma 2 a2, or else you'll have one more formula, that is sigma 1 by e1 plus sigma 2 by e2 is equal to t into alpha 2 minus alpha 1. So by making use of those two equations only, you are going to calculate the various values. Next, so we have also discussed temperature stresses in a simple bar. So if yield is not there, then compressive strain is alpha T. Then stress is E alpha T. And the compressive load is AE alpha T. Next, if there is a yield permitted there of delta, then the compressive load, the compression is L alpha T minus delta. Now strain is alpha T minus delta by L. Next, temperature stress is E into alpha T minus delta by L. So in this manner, we are going to calculate the values when exposed to the temperature. So in tomorrow's class, we will be going to the temperature stresses, stresses due to the tightening nut and temperature rise. Here you are considering same both. Okay. And we will finish up the chapter by tomorrow. Okay. So thank you all. Thank you very much.